Okay, so I'm gonna quickly go over term symbols and give you some background information on spin. Um, and so we have spin. When it comes to spin, we have S. We call it S for spin, and we have the absolute value, which can only be half. And I say absolute value because we have two possibilities for m sub s, which is the momentum. You can think of spin, um, and that's plus or minus half. So electrons can move up, which we consider as half. It can move down, which is negative half. Um, and so the whole point is that now we have the Pauli principle I can introduce. And the Pauli principle basically says that we have this operator, p hat 1, 2, acting on the psi function, and it's equivalent to negative 1 times psi tot. And one thing to note is when it comes to these wave functions, we have symmetric and antisymmetric wave functions that are possible. And so let's say, for example, that we have a symmetric psi tot that translates, if it's symmetric, to plus 1 times that. But if, let's say, it was antisymmetric, if it was this, then we have negative psi tot. A. And so this means that in this case, according to the Pauli principle, that psi tot, the wave function, must be antisymmetric since it follows this. And so psi tot is antisymmetric, and it's also equivalent to psi space times psi spin. And so the rules of symmetry are that if we have the product of two symmetric functions, it's a symmetric function. Same thing if it's the product of two antisymmetric. The only way you can get it, oh, sorry. This is supposed to be, let me just undo. Sorry, the product of two antisymmetric functions is also symmetric. But the product of a symmetric and an antisymmetric is the only way you can get an antisymmetric. So for psi tot to be antisymmetric, one of these two must always be antisymmetric. And so that's the case that you need to know coming into this. And then, so the one thing to know is I'll talk about what are the, let's say that psi space is symmetric. What does it look like, right? Well, that equals, let's say in this example that we have an electronic configuration of 1s1 and 2s1, right? This is an example. What would a symmetric psi space look like? Well, it would be psi 1s, the first electron, psi 2s, plus the second electron times the first electron. So this is what symmetric psi space would look. If it was antisymmetric, we swap out this plus with a minus. That's it. That's what makes it antisymmetric. But when it comes to psi space, right, we have different possibilities. So let's say that psi spin, right, let's say that psi space was antisymmetric. We had that negative in there. That means that psi spin must be symmetric. So what does a psi spin symmetric look like? Well, oh, I should introduce this. M sub s equaling positive half, we denote psi spin equals alpha. And if it's negative 1/2, then psi spin equals beta. And so here, if it's symmetric, there's three possibilities that psi spin could be. Alpha alpha, both of the electrons are up. Then we have 1 over root 2, this is a normalization constant, times alpha beta plus beta alpha. And then we have beta beta, both of them are down. So this is the case that one of them is up and one of them is down. And then what happens if, let's say, psi spin is asymmetric, right? Well, it's very similar to this middle case. This equals 1 over root 2 times alpha beta minus beta alpha. So that's what that looks like. Yeah, and so that's basically the stuff you need to know. going into term symbols now. So basically, when we're dealing with these large multi-electron stuff, you can think of it as our lowercase m sub s turns into uppercase m sub s, our m sub l like this turns into just some like nomenclature, turns into this. So basically what I'm saying is that L equals this, S remains as S, it's just a capital version of itself, and then we used to have a J and that turns into J. And J is a vector sum of this. You can think of it as basic. We'll say that it's L plus S, but it's the vector sum of these two. And so the way how we denote term symbols is 2s plus 1 L, so it's this L, right, with the subscript of J, so the vector sum of this. And so we'll see, so like an example of this would be 1s0, right? So this is where we have s equals 0, L is equal to, a singlet, so it's s, and then we have J is equal to 0 because L is 0. So when L is 0, we have S. When L equals 1, we have a P. And then when we have L equals 2, L equals 2, we have a D. And then that turns into sigma pi delta if it's a molecule, basically. But now that we have all the background information, let's get into the table that we'll be using. And so term symbols, basically what they're trying to do is they're trying to denote sets of wave functions that are degenerate, right? So like the same like degenerate wave functions. And so I'll give you an example. Let's say that we have electron configuration of ns2, mp2. And the reason why I have n and m is because these actually don't matter, these numbers in front. We just care that we have this p orbital now. And so now we have a complication because unlike the s orbitals before, p orbitals are not just one. We have px, py, and pz. And so we'll denote that. Let me pan a little bit down. So we have px, pz, and py. And we denote the n sub l values for these as 1, 0, and -1. And then I'll write capital M sub L as the amalgamation of the different possibilities that I'll be drawing. And then we have an M sub S, which we'll be looking at the spin. And so the point here is now I'm going to be drawing out all the possibilities that we can have 2 electrons in the p orbitals. So we can have, both of them being up, and these lines are supposed to be straight, but excuse my drawing abilities. And so we have this, and then we have the opposite, right? Like inverted kind of. And then we have both of them being down. And then we have also the possibility that both of them, both the electrons, are in the same shell. So we have this as another possibility. So overall we have 15, right? 3 times 5, 15 different possibilities. So now how does this help us, right? That's the whole point. How does this help us? So what we'll be doing is we're going to first calculate what m sub l is, capital this. And so how m sub l is basically you multiply, you can think of it as multiplying the number of electrons in this shell, or this subshell, times its m sub l value. So in this case, it would be, we have 1 electron here, right, as opposed to like 2. We have 1 electron times this value, so 1 times 1, plus 1 times 0, which is 1. So we have 1 here. Here, it's 1 times 1 times 1 times -1. So it ends up being 1 minus 1. So it's 0. And then you can calculate for yourself is -1. And we see this repeated. In this one, we have 2 times 1, right? So it becomes 2. So you'll see that this one is a little bit special. It has 2 and 0 and -2. Now, how do we calculate m sub s? Well, we add up the spins. So both of these electrons in this box are always going to be up. So we have up is half, positive half. So we have half plus half, so it's 1. And so everything in this box is always going to be 1, 1, 1. In both of these, we have opposite signs, right? We have half, one of them being up half, and then one of them being down half. So we're going to have 0, 0, 0. Same thing for this one. And in this one, we're going to have -1, -1, -1. And then we have, in the same orbital being counteracted. So we're going to have zeros for this. So now that we have all this, we want to figure out, what are the different term symbols that we have. And so as I was talking about, if L is 0, then we have the only values that it could be is 0, right? Grouping wise. We have L equals 1, we have -1, 0, 1. If L equals 2, we have -2, -1, 0, 1, 2. So we basically want to group these different possibilities into these. And so let me use different colors now. We'll call this possibility. Oh, did not mean to do that. We'll call this possibility. We'll call this X, and we'll write in red. This possibility, we'll call this Y. And then I need a third color. We'll call this blue. Okay. And then this possibility will be Z. And so we have X, Y, and Z. And we want to be able to group all of these into one of these. So let's do that. So let's first start with X. So we see that we have a grouping. This is all for M sub L, by the way. All these groupings. So we see we have a 1, 0, -1 here, right? Oh, sorry. Not for M sub L. Sorry. Go back. So we have these. These are the S values, by the way. So we have a grouping here of 1, 0, and -1. So these are all going to be X's. And we see this repeated again here, here, and here. So we have these also being X's, and again, same thing here. So we have a lot of X's. So now that we see this, we can also group, we could have done this from this, that all these are 1, 0s, and -1s. So now we have all our X's. Now let's go look at the Y's. So we have we found a 2, right? We found a 0 for it. We found a -2, and oop, did not mean to do that. Let me just zoom. So we have 2, 0, -2. We now need to take a 1 and a -1, and the only ones remaining are from this box. So we can take this and this. And so now we're going to denote these Y. And then finally, all that's left is Z, which is 0, right around here. So now we have our X's, Y's, and Z's. So now what are we going to do with this, right? Well, now we apply the term symbols. So let me go to X, or yeah. So we have, first what we want to know is how many pairings do we have? We have 1, 0, -1. True, we have one pairing, but we have 3 copies of that pairing. So what we're going to have in the term symbol is our superscript is 3. And remember that superscript, let me scroll up. Our superscript was 2s plus 1. So we have 3 pairings, And this number equals 2s plus 1. So that means that s must be 1. So we have s equals 1, right? And then L equals 1 as well, because we have this pairing, L equals 1. This is what X is, so L equals 1. So what that means is, if L equals 1, I told you that this becomes a P. And now we have the different options that it could be. It could be 2, 1, 0. Because this bottom number is J, which is the vector sum of L plus S. So we have 1 plus 1, which is 2, but we also have, what if it was 0? So we have 1 plus 0, which is 1, and then we have the 0, 0 plus 0, which is 0. So X term symbol is 3p210. Now let's move on to Y. So now we have Y. And how many copies of Y do we have? We only have 1 copy. So we write 1 in the superscript, and that means that S equals 0. So we have S equals 0. And so now we have L equals 2 though, right? Because the Y pairing was this. And this is when L equals 2. So we have L equals 2. And so now we have this being D. When L equals 2, it becomes D. When L equals 1, it's P. And 0 is S. So we have 1D. And here we only have 1D2. Here. And then lastly, we have Z, which is blue. Okay, and then for this one, we also have only 1 pairing. And remember that it's Z was this. Here, let me zoom out. Z was this one where L equals 0. And so S equals 0, L equals 0. That leaves us with, let me write that. S equals 0, L equals 0. So this is 1s 0. That's what Z is. So now that we have the term symbols, what's the whole point of the term symbols? Well, the term symbols now help us use Hund's rule. So we're going to use Hund's rule. What is Hund's rule? Basically, Hund's rule says that when we're ranking by energy, we go from low to high, right? And the first criteria is we want to have max spin, angular momentum. The second one is we want the same thing, but now for orbital angular momentum. And then third, right, we have if the shell is less than half full, J min equals J. And then 4 is if the shell is more than half full, J max equals J. And so this is a little bit complicated, but we'll see it in action. But if I was to basically draw the Hund's rule denoting the energy placement for this, it would be something like what you would draw first. So since we have 3 term symbols, it would be something like this. And then basically what we do is which one has the maximum angular momentum. If we go back to this one has the max, right? So we're going to put 3p210 in the bottom one. So it's 3p210. And then the middle one, we're going to put orbital. This letter is the orbital. Which one has the most? D, because D is L equals 2. So we're going to put the 1D2 here. and that leaves us with 1s 0 here. And so this is using Hund's rule to place all of these like this. And this is like, these term symbols are basically denoting all degenerate wave functions. And so like for each of these term symbols, you can imagine we have psi tot equals psi space times psi spin, and we have, you know, the different possibilities. You know, if it's like odd, then we have, you know, if it was like 1, like for this one per se, right, 1s 0, then we have symmetric psi space, anti-symmetric psi spin, and so you can already imagine, right? So like this one, this one is always going to be psi space, symmetric, and then psi spin, anti-symmetric. And so you can already write the wave functions for this. And then same thing for this. Now that we have the term symbol, we can write these wave functions as, you know, if it's symmetric or anti-symmetric. And yeah, that's it.